and on Monday would be the Ka of a monoprotic acid. So we're delaying before we restart the ester lab, trying to give that long enough to actually get to equilibrium. Okay? How many of you prepared the pre-lab for this one? Oh, it looks like mostly everybody. Okay, it's not too bad. Because it's definitely confusing over which lab you're supposed to have prepared. So as far as what we're going to end up doing, it's ultimately going to be very, very beneficial for those of you in lecture, because it directly correlates to what we ended lecture with today, which is ultimately looking at titrations and buffer solutions. All right? So to start off with, what we're going to try and discover is the Ka, or the acid dissociation constant for a monoprotic weak acid. Okay, so that's kind of our goal. So things that we would need to address in the title. Any ideas? Good first place would be probably Ka. What else? Monoprotic. Be another good word to throw in there. How are you doing? You're doing a titration. It's not just a standard titration with a color change, though. You're looking at a pH titration. Okay? So kind of all the important key words that should show up within that are now shown as well. Okay? So somehow organize those all into a coherent title. One of the other things that you will end up determining in the process of this reaction is the molecular weight for your weak acid as well. So you could tag that into the title. Okay. As far as the report goes, so I want to address this, at least based on these last two reports I've graded. Remember, on Canvas, there's a little file, and in that file it says what things you need to write for each report. Okay. Every lecture that we've gone through has also said what you need to write for each report. You are more than welcome to write the entire report, as several of you have done. The fun thing about writing the entire report, I'm not going to read it. Okay? The only things that I'm going to go through and read are the things that you're responsible for. Okay? So for this report, you're looking at the title, your method section. So it's the first method sections to go through and write. Which, believe it or not, this one actually won't be too bad. It may look long, but it's actually a fairly short one to put together. Your results and calculations as always, and then your discussion conclusion. Okay? I will be passing back your reports, particularly around the discussion and conclusion. The second lab, the scores were much lower than the first lab, and I think all of that came in the discussion and conclusion. So I think there was a lot of confusion over writing that discussion and conclusion. So look at what things were addressed when you look at the reports and make those changes for when you actually have to write this one. Is that a hint? Okay. If you submitted it via email, those are always slower for me to get grading, so I will try and get those back to you by the end of this week, but we'll kind of see what happens there. Okay. Introduction. So what things would you need to address in an introduction, which you're not writing for this one, right? Yeah, not writing for this one. To start off with, we need to address some of these things because they're going to have to show up, or to a certain extent, they're going to show up in the discussion as they pertain to your result. So when you write a discussion, you need to address the important aspects of the introduction and how they affected your result. Don't rewrite the introduction. That's not helpful. Okay? The intent of the discussion is to take the important parts of your introduction and directly tie them to your results. If you don't have that direct tie, it's going to get crossed out, and you're going to be told to put it somewhere else. Okay? Not meanly, like put that information in the introduction. Okay? Just want to be clear. So why we end up doing this one? We want to find the Ka and the molecular weight. So a good thing to show up in your introduction would be, the discussion conclusion, the Ka and the molecular weight, okay, your actual results. I do ask, and this is maybe slightly different from what you'll see in future classes, that you repeat your results in the discussion conclusion. Okay, and that comes largely from how I grade your reports. I don't grade reports beginning to end. I grade individual sections of the report. So if you think your results are important, and they are, they should be mentioned in the discussion conclusion. Okay? If you don't mention them, that means I spend more time grading because I have to go back and find what your result was to give you a grade. The longer I spend grading, the more accurate I become. Unfortunately, that usually means less points for you. Okay? So you want fast grading where I'm not paying attention to what I'm doing. You get more points. Okay? So try and write your reports as easy as possible to be graded, and you will get higher scores, regardless of whether or not they're right or not. Okay? Just because that's how it works. Okay? So why is it important to go through and do this? Knowing the Ka of an acid, we could use that as a buffer system. So if we know the Ka, we could decide for a particular reaction, we want the buffer pH or balanced at that range. Okay, so it can be helpful in that case. They're both important characteristics of an individual acid. So if we do have an unknown acid and we want to identify something about it, the Ka is helpful because we get an idea of its reactivity, and then the molecular weight is helpful because that gives us an idea of what the acid is. We could start to extrapolate structural information from that, or formula information from it. Okay, so those are really important aspects for this experiment. So how do we end up doing it? Okay, well, to start off with, we want to test its reactivity. So if it's an acid, what do acids react with? Bases. So what are we going to do? We're going to add base. And we're going to monitor how it reacts with that base through the course of some arbitrary measurement. In this case, we're going to monitor how it responds to that base with respect to pH. So how does our weak acid control the addition of base? Okay, so that's going to have to happen through a titration or a pH titration. Before we can do that, we need some way to evenly add the base. How could we add the base? Drop the base. Right. We could go through and measure it by hand, do very small solid amounts, but that gets tedious. Or we could do it in a liquid form or in solution. So the first thing we need to do is make our base solution. Okay, so it has to be a known base. Okay? And what we'll do is then slowly add the base and monitor the pH. We can then generate a titration curve. That titration curve we can then pull information out of. Okay? What information or what things complicate this? That base solution, we need to be super accurate with its concentration. So just weighing out the base isn't going to help us enough. We have to standardize it, so we'll titrate against some known standard. The standard that we're going to use is known as KHP, mainly because we're trying to show something of its chemical characteristics while not having to spell everything out. KHP is potassium hydrogen phthalate. A better way to look at it, particularly in the case of a balanced reaction, would be HKP. What happens when we add base? We get water and Kp minus. Okay? So what we're going to end up doing is measuring out a known amount of KHP, dissolve it in some water, and slowly titrate our base solution into it. Okay? We'll use phenolphthalein as an indicator. What happens when the indicator changes color? It's not that it's at equilibrium. What did you say? It's the end point of the titration. What happens at the end point of our titration? The moles of our potassium hydrogen phthalate equal the moles of OH minus added. Okay. Which then allows us to determine our molarity. Because if we know how much KHP we added, we now know the moles of hydroxide. Why do we know it's 1 to 1? from our balanced equation. Okay? So by running that titration, we can figure out the exact moles of OH minus, okay, in our solution. How do we get the volume to get our molarity? How did we get the OH minus added to the solution? Through a burette. With the burettes, they're all marked with volume on it. We can then divide our mole amount by the volume of water added, or the volume of our solution. And we've got the molarity of our base solution. Okay? That molarity we will report out to 4 sig figs. So as many significant digits as we can get. So that way when we translate or use this information later on, we can get the maximum amount of significant digits in our Ka value and in our molecular weight. Okay? So that's what happens at our endpoint. So that's what we're going to do today, is just run that titration. At least that's minimally what we're going to do today. Okay? That titration, particularly if you're good at it, won't take that long. We'll repeat that trial 3 times, and actually we're going to change it to 4. We're going to do that titration 4 times. Okay, any idea why 4 times? Because you're working in partners. So what we're going to do is make 1 base solution per partners. Okay, you will each titrate twice. You can then swap data, average your results, and you've got the molarity of your base solution. If you're planning on working by yourself, you get to do 3 trials so that you can do a reasonable average. Okay? At that point, you could be done. Again, depending on your skills titrating and how you make up solutions, you might be able to finish that part within an hour. And since we aren't going to talk much longer than this, you could then move on to the second part of the experiment, which is what's planned for Monday. If you finish the second part of the experiment, you're done entirely with the experiment, which means you could either skip Monday, or you could come in Monday with a laptop or claim this computer and do your entire lab report. What is it, Thursday? I'm sorry.
Tuesday.
Whatever. Thursday, you could then skip. Okay? So if you finish the entire experiment today, you don't need to show up Thursday. Okay? That said, you have to be very careful with how you go through your titrations, and you have to be fast and effective. Okay? Some students are really good at going through and rushing through and getting it done. Some students aren't. Okay? I'd kind of leave that up to you to decide which category you fall in. If you don't feel confident rushing through it, then don't rush through it. You've got 2 lab periods to do it in. If you attempt to go through and do the whole thing today but don't get it finished, guess what? You still get to show up Thursday. Okay? When it comes to the pH titration, everybody does that individually. Okay? So you will do 2 standardization trials and 1 pH titration. Every single person does. Okay? That will help out at the end, because then you can compare your results of your pH titration to your partner, and they should be the same. Okay? If they're drastically different, when we go through, or when you go through and determine the calculations, we can try and figure out who did it more correctly, and you guys can use that 1 set of data. Okay? But everybody should go through and do that whole titration. Okay? From the curve, your pH curve, what we're going to end up doing is interpreting something known as what I've abbreviated here as the HH equation, or the Henderson-Hasselbalch equation. It's a really helpful expression that we'll talk about in lecture tomorrow, but you guys will get a brief shot at it here. Okay? And it allows us to solve for the pKa very, very readily from the titration curve. So it's kind of nice for that respect. So I think that's all I wanted on there. So to standardize, you're going to need to make up a sodium hydroxide solution using solid sodium hydroxide. What's fun about solid sodium hydroxide?
Yeah.
it reacts with water in the air, which means its concentration effectively changes just by measuring it out. Okay? Which means we have to go through the standardization procedure. Otherwise, we wouldn't get an accurate result. Okay? Because our mass would end up changing because it's absorbing water. The other thing that's fun with solid sodium hydroxide, not only does it react with water in the air, it reacts with your skin. Okay? We talk about concentrated acids and we think of solutions. Most bases are extremely ionic, meaning bases in their most concentrated form are solids. Picking up sodium hydroxide solid with your bare hand is a really bad idea. Please don't do that. Okay? The other issue with it is because it's so concentrated, it does tend to destroy things like the whey paper. So what we're going to end up doing is massing it on an actual balance. They call it the triple beam balance, I guess, where you put weights on one end and balance it out, old-fashioned tiny thing, to get the NaOH. Because if we did it directly in our fancy balances with the electronic ones, it could ruin those instruments. Okay? In your pre-labs, you have already calculated how much solid sodium hydroxide to measure out, right? How much solid sodium hydroxide are you supposed to measure out? What's that?
2 grams.
2 grams. Does that look suspicious? Oh, 2 grams. I get the same answer. You need to measure out 2 grams. They are measured out as solid pellets. Getting an exact 2 gram amount is approximate. So we don't care that you get exactly 2. We want approximately 2. Okay? So since all the pellets are roughly the same size, one person can measure out 2 grams and then be really nice and tell everybody else how many pellets that was. Then nobody else has to measure it out. They just count out the pellets, put it into their water. Okay? You'll then go through and dissolve that in 500 milliliters of water. Make sure it gets entirely dissolved. That may take a little bit of time to get it to mix. Yes?
We're doing 500 instead of the label 400?
It says 400?
Oh, I'm so sorry. I'm reading it like 400.
Okay. I mean, it's possible. I don't actually read it. That's not quite true. So you'll make your 500 ml solution. Make sure those pellets get entirely dissolved. You will probably notice that the container gets hot. Why would it get hot? Not isocaloric. It's an acid-base reaction. Acid-base reactions are exothermic. Is that what you said?
Yeah.
Oh, I heard isocaloric.
Exothermic.
Yeah, it is an exothermic reaction. Good job. Which it means when you add the base to your water, it will generate some heat. The solution will heat up. We don't want that solution to be hot when we do the titration. Why? Could potentially change the dynamics of our reaction. Okay, so mix it up as best you can. I wouldn't worry too much about it unless it gets too hot to handle, which it shouldn't. But be aware of that. Okay? The next part is that you will then titrate the solution against KHP. Okay? Which brings up an interesting question. Why do we use KHP? You're going to mass out your KHP for your standard solution. So you're going to weigh it out. You're going to make a solution for it. Why not use something like HCl? Okay, because it's any acid. Why do we use KHP? HCl, if we tried to weigh that out, so let's just pretend we weigh out HCl. Let's say we can get it into a solid state. Okay? And we make a small measurement error in the mass of HCl. Say instead of measuring out exactly 0.1, we measure out 0.11. How much of a difference in moles does that make? We'd have to go back and look at the molecular weight. So our error was 0.01 mass with respect to the molecular weight of HCl, which was 35 grams per mole, 36 grams per mole. So we're looking at 0.1, what is that, 0.1 times 36? 0.01 times 36? So it's a pretty reasonable number. If we go through and look at KHP, it's actually 0.1 divided by 36. Sorry, I did the calculation wrong. If we look at KHP, what's the molecular weight of KHP? A lot bigger. So when we make that same 0.01 measurement error, what happens to the amount of moles? Doesn't change the mole amount as drastically. So when we're going through to standardize a solution, we want to pick a standard acid or base that has a massive molecular weight. So that way, if we do make mistakes in weighing it, those mistakes are minimized because the molecular weight is so large. When we're doing our titration, remember our endpoint is mole to mole. We don't care about the mass, it's all about those moles. So a small error in weight with a small molecular weight generates a relatively large mole error. Okay? So we're going to make up these KHP solutions by measuring them out. This is again something that you should have calculated in your pre-lab. What do you think the number is? 0.7 grams, roughly. I think it comes out to 0.714 or 41. I don't remember. As long as you're close to that number, you should be okay. Make sure you record it as accurately as possible, whatever the balance tells you. But we're looking right about that 0.7, a little bit higher than that. Okay? You'll go through, I know that says 3. We'll do 2 per partner. If you're good with your timing, this is how we can get out of lab faster, because each partner will be doing the titration simultaneously. Okay, so you'll go through the experiment a little bit faster. Okay? We do not have to know the molarity of the NaOH to continue with the experiment, the exact molarity. Okay? Because we know what it is approximately already. That's why we measured out 2 grams. Okay? So you don't need to know that number to start the pH titration. Okay? At this point, you would officially be done, so you could go home and calculate it. If you decide to stick around, you won't keep the solution in your drawer. You will immediately move on to the next part. Okay? If you do decide to leave, you just label it in your drawer, label the bottle, put it in your drawer, and just kind of hold on to it for next week. What you'll do now is go back to the stockroom, get your unknown, a burette, and a stir bar. Okay? Because you will need the burette anyway, you might as well go to the stockroom and pick this all up now, just because you can. Okay? Because everybody's going to need a burette, everybody's going to need a stir bar, everybody should get one of each of those. You only need 1 unknown per group of people. Okay? Again, it's up to you, but you only need 1. You'll then need to make your unknown solution. Okay, this is technically part of the pre-lab for day 2, which would be Thursday. Did anybody actually calculate it? Anybody know what it's supposed to be? 5 grams. So if you weigh out approximately 5 grams of your unknown, you'll be set with your solution. You need to know exactly what you measure out. It should just be approximate to that. Okay, because you're both using the same unknown. You might measure out your unknown, figure out what its total mass is, and just divide it in half. Okay, so it may not come out at exactly 5. It's not that big of a deal. You'll then move to using the pH meters in the back room. Now that I think about this, let me check, make sure we actually have those set up. Yes, we do have the pH meters ready to go, so you are good to use those today. You will then go through, set up your burette. All of them should be set and ready to go. You'll put your sample of your unknown acid on the spin plate, start it stirring, and slowly add your base. Okay? You will record a 0.2 pH change. So you'll add enough base to cause a 0.2 change. Once you've gotten that 0.2 change, record whatever your volume is. Okay? Then continue to add until you get that 0.2 change. Do it again and again and again. To start off with, it'll probably take 1 to 2 milliliters of base, okay, to get that 0.2 change. It will eventually get to the point where if you add a drop, you jump from, instead of it being a 0.2 change, to maybe a 2 change. Okay, why would it change so rapidly? There's no buffer. Okay? As we've slowly added that hydroxide, we're slowly reacting with our monoprotic acid until eventually there's no more acid for the base to react with, which means all we're doing is adding hydroxide. The pH is now going to spike very, very readily or very rapidly. Then it's going to level off again. Okay? What I'd recommend you do is that when you go through this process, you might need to use your full burette. You might even have to double down and use a burette and a half of volume. Okay? Kind of just depends on the reaction. What I would recommend is that you get up to that 1 to 2 range again. Okay? 1 to 2 mils to get the pH change. I believe from last summer, a good end point when you can stop doing the pH titration is about a pH 12. Okay? Roughly. Okay? That kind of depends on the individual experiment. Kind of get a feel for how your pH is changing. If that pH change is very small, then you need to keep going. If it's the pH change, no, sorry, let me try that again. If the volume change is very large to generate a small pH change, you're done. Okay. How much do I want to go through and do this? Solving for the Ka. So let's take a look at this real quickly. This will be some algebra stuff to see what's happening with our Ka. So let's write out a Ka expression to start. What is the Ka for this reaction? Okay. So we would need to know the concentrations of all of these species to be able to figure this out. That is something we could potentially do. Okay. But we want to try and work smarter, not harder. In the process of doing this, what are we monitoring? What are we monitoring during our titration? The pH. pH is, how do you determine the pH? The negative log of our H3O+. Okay? So to do that, what we'll go ahead and do is say, instead of trying to solve for all of these things, let's just try and jump the gun straight off the bat. Let's get our pH showing up in the equation. How can I get pH to show up in that equation? To get a pH, what do I need to do? Negative log of H3O+. So how can I get pH to show up in my equation? Let's take the negative log on both sides. So I would get the negative log of the Ka equals the negative log of this big awful mess, which I'm going to abbreviate. Before I do that, because it's going to be a little bit shorter if I do it this way, I'm going to pull that H3O+ out a little bit. It's a very, very small change. It just shortens what I have to do later. Okay. Now when I take the negative log of both sides, I get the negative log of the Ka equals the negative log of H3O+ times this stuff, one of our distribution factors with logs. Anybody remember? The negative log of something times something is the same thing as the addition of those species. So I can distribute that negative log through oops, that's an A. Man. Hi. What's the negative log of the Ka? Or maybe let's try it a different way. What's the negative log of H3O plus? pH. What's the negative log of Ka? The pKa. Okay. Minus the log of our concentration of A minus over HA. Okay, there's a couple different ways we can manipulate this equation, but this one works well enough for what we've got right now. Why is this equation going to be helpful? If I want to solve for the pKa, I know it is related to the pH, okay, but I have to account for this big old nasty term. We could go through and try and plot it as a straight line. There's another way, though. What happens if the concentration of A minus equals the concentration of HA? Get 1. What's the log of 1? 0. When that occurs, the pKa equals the pH. When are the concentrations of A minus and HA the same? Is that because you don't know the answer, or you want me to say it? What happens at the end point? The end point of our titration. What did we say happened? How much HA is left? So if we looked at a titration curve, we'd start at a low pH and it would flatline and then spike. Our end point is where we transition. What happened at that end point? How much HA is present? None. That's why it's spiking. Because as we add the base, there's nothing to react with it, so the pH spikes. Okay? What's the concentration of A minus at that point? What happened to all the HA? It all reacted to become our A minus. Okay? So at this point, our HA equals 0, and our A minus equals what our HA started with. Okay? I want the position where A minus equals HA. What can you tell me about our initial point? Way down at the very front. Orange was a bad color, let's try green. What can you tell me about our green point? What's present at the green point? Only HA. So what's our concentration of A? 0. I want where they're equal to each other. Where are they equal to each other? Halfway in between, known as the half equivalence point. At the half equivalence point, I know that the concentrations are the same, which means this expression simplifies to saying that pKa equals the pH. So given this titration curve, if I want to know the pKa, what I'll go through and do is say, okay, to get to the equivalence point, it took this much base. The half equivalence would be half that amount. I would now go up to my curve. The pH at that point happens to equal the the pKa. We will talk about it again on Thursday. All right? So we can determine the pKa by evaluating what's happening on our pH curve or our titration curve. That's why we go through and play with that curve. Okay? It allows for us to determine that value. So it's kind of nice. Okay? Questions about that right now? Okay. All of that comes from, well, most of that comes from the algebra of manipulating your Ka expression to end up with this key expression at the bottom, which your book may manipulate a little bit. This expression is known as the Henderson-Hasselbalch equation because it was Henderson and Hasselbalch that happened to discover this relationship. Okay? They first noticed it and said, hey, this is cool. Okay? That A minus equaling HA comes from being able to understand what's happening at our green and blue points. What things are present. If we want the point where they equal each other, that has to be halfway between transferring completely across. Okay? That will give us our Ka. This has lots of information on it. At the end point of our titration, so right where our curve spikes, what can you tell me is true about that point? We just talked about a couple of things. It doesn't necessarily have to be neutral. There's no HA, so our moles of HA equals 0. How did they get to 0? How did we get rid of all of the HA? We reacted it with the base. So at that point, we know that our initial moles, HA, equals the moles of base added. Can we determine the moles of base added? How do we determine the moles of base added? What do we know about our base? We know the molarity based on our standardization, which was at 0.7. So it'll be roughly 0.7 moles per liter. Oh, that's molarity. We want moles. So what do we need to get rid of? Liters. How do we get rid of that unit? Multiply by liters. But what number do we do there? Liters of what? Base to reach what? The end point of our reaction. So this will be the volume to reach the end point. That gives us our moles of OH. What does that tell us about HA? Tells us our moles of HA. If I want the molecular weight, to get the molecular weight of my acid, what do I need? What units are there on molecular weight? Grams over moles. What did we just find? The moles. So we need to get the grams. How do we get the grams? We weighed it at the beginning. And we now have the molecular weight of our compound. Okay? So in this experiment, we're taking advantage of 2 points. The end point and our half equivalence. All of our calculations hinge on being able to determine the end point as accurately as possible. Okay? So when you go through and do your titration, you want to make sure that you get lots of points on this vertical line, which means very, very small volume changes. Okay? The more points you can get on that line, the more accurate your results will be, the more points you get on the lab report. Okay? Your lab notebook procedure thing goes through and helps or provides 3 methods for determining that endpoint value. I do expect you to do at least one of those methods. We'll talk about that on Thursday again once we have data. Okay? So at that point, I'm done talking, unless you guys have questions.